Hello everyone. Welcome to the lecture on design of solid slabs. First we'll discuss one-way slabs. One-way slabs, as previously mentioned, are slabs in which there is one main direction in which the load is transferred, and this direction is the main direction at which the reinforcement will be placed. However, the secondary direction or the other direction is containing only minimum speed. And this main direction versus secondary direction configuration is done mainly because one of the two dimensions is more than double the shorter dimension. So the longer dimension is more than double the shorter dimension as shown here, where L2 is more than double L. But in order to understand this, why is this happening? This is because when the shape will deflect, as you could see here, there is a very major difference in strain between both directions. So this is how it could look. It will deflect if it is simply supported, and this is how it will deflect if it is continuous. In order to dimension one-way slabs, simply we calculate what's called the effective length or the effective span, which is the smaller of the clear span plus the thickness if it is a cantilever, and the actual span L, or the if it is simple or continuous slab, it's the clear thickness plus TS and 1.05 the clear span, but it should not exceed L. The minimum slab thickness is the larger of 120 millimeter and span over 10 for cantilever slabs, span over 30 for simple slabs, and span over 35 for continuous slabs. The minimum concrete cover is 20 millimeters. The moments on one-way slabs are simply calculated by first calculating the ultimate load, which is 1.4 the dead load, which is the flooring plus the slab thickness times the concrete open weight, plus 1.6 of the live load. So what we do here is that we take a strip, a 1 meter wide strip, and deal with it as our beam. So because of that, we will take this pressure, the ultimate W ultimate, and multiply it by the effective L square over K. This K is 8 for simply supported slabs at the midspan and 24 at the supports. If we are talking about two span slabs, we are talking about a 10 at the midspan and 8 at the middle support and 24 at the edges. If it is three or more spans, the maximum is 10 at the first bay and 10 at the first inner support, then 12 at each bay and support after that. In special cases, the Egyptian code requires additional consideration if the spans are significantly changing, because if the spans are significantly changing and you have this situation at which you have a midspan which is very small, then you should reinforce it upper and lower reinforcement, because in some cases it will be having maximum positive moment, and in some other cases you'll be having maximum negative moment, so you should take account for both. And of course, in case of heavy loading, you should also consider this issue. As discussed before concerning the rebar, there should be an overlap between the upper and lower rebar in the following manner. As you could see here, there should be an overlap of L over 20 or 0.7D or 10.5, whichever is longer of them, when you overlap the upper and the lower reinforcement. Let's take an example here. Here you have a three-bay slab, one-way slab. The flooring weight is 1.5 kilonewton per meter square. The live load is 3 kilonewton per meter square. FCU is 30 megapascal. Fy is 400 megapascal. The beam width is 250 millimeters. The solution here, the dimensions, since the slab is continuous, T minimum is 3000 millimeters over 35, which is 86 millimeters. So this is far less than the 120 millimeters. So you should take it as the 120 millimeters. The clear span is 3 minus 0.25. This is 0.275 meters. If you add this to 0.12, you will get 2.87. If you multiply it by 1.05, you'll get 2.89. So this is more than 2.87. But again, all of this is less than the 3 meters. So L effective is 2.89 meters. By the way, if you are in a hurry in an exam or something, you don't need actually to calculate the L effective and that stuff. You could just take the L effective as the 3 meters, because as you could see, the difference between 3 and 2.9 is not that major. So if we go and calculate the ultimate load, 1.4 times dead plus 1.6 times live, we reach 11.1 kilonewton per meter square. Taking a strip width of 1 meters, the load acting on this strip is 11.1 kilonewton per meter. If we go and calculate the bending moments based on this configuration, as we have 3 spans, you'll find that you have here a 9.25, a 9.25, a 7.71, 3.86, but the maximum two sections are 9.25 and 7.71. Actually, because both are rectangular sections, 9.25 here at the first mid span and 9.25 at the first inner support, they will have the same reinforcement, however opposite direction. What will be a little bit less is section number 2, which is at the middle mid span. So when you design something like this, because it's a rectangle section, the 1 meter strip has a width of 1000 millimeter. D is 120 minus 25. This is 95 millimeters. The AS minimum is 0.6 BD over FY. This is 0.6 times 1000 times 95 over 400. This is 144 millimeters square. If you take a section 1, the R1 is M ultimate over FCU BD squared. We are using this R1 omega technique, the charts and the tables. So if you go and calculate this ratio, then you go and compare it, you get the graph. Omega is equal to 0.041. So omega multiplied by BD FCU over FE, this gives us the area steel. This is 292 millimeters square, which is more than the minimum for sure. So 2.5 phi 10 and 2.5 phi 8 per meter are enough. Somebody could ask, how could you place 2.5 and 2.5? You could not place half a bar. Actually, you go and measure a strip of 2 meters. You place 1 bar over 10 and 1 bar over 8, then 1 bar over 10, then 1 bar over 8. So 5 and 5 staggered bars between in the 2 meter strip will give us 2.5 phi 10 and 2.5 phi 8 if we are talking about a 1 meter strip. Section 2, if we are talking about section 2, we take a section and we compare the numbers. R1 is less for sure, it's 0.028 compared to the 0.034. Omega will be less, it's 0.033. Then if you calculate AS, for sure it's less, it's 235 millimeters square. So this is actually 5 phi 8 per meter is sufficient enough. The details of something like that. In such a case, the details, your x-axis here is the main direction. So 2.5, you could look at the first thing here, at first bay, 2.5510 and 2.558, and then you bend the bars. You bend the bars in order to bending the bars, by the way, in Arabic they say يكسحوا السيخ. السيخ تم تكسيحه. Okay. So when you bend the 2.5510 from one side and 2.558 from another side, you get the same result, 2.5510 plus 2.558 above the support. Then at the midspan, it's 2.558 and 2.558. Because it's symmetric, the thing is repeated on the right hand side. However, from the other side, the secondary dimension, you have 558 per meter, which is the minimum reinforcement that you need. And again, you must have this bending of bars at the end supports. Two-way slabs, they are very similar, by the way, in terms of detailing. They are very similar to the one-way slab. Doesn't make a difference at all. Okay, the only difference is that you are having more steel at one direction than not just a minimum. However, in terms of calculations, they will differ because the slab is considered two-way if the ratio between the two sides is less than 2. Therefore, both are contributing. The x and the y axes are both contributing in resisting the load. So if you could notice here, this deflected shape represents this behavior, that both dimensions are contributing. It's not one direction that is mainly contributing and the other is doing nothing. No, there is one carrying more than the other, but not the other is not just carrying zero. So the load distribution is function of the rectangularity ratio. This rectangularity ratio depends on there is a factor m and per direction. And there is the dimension. So if one direction is simply supported and the other is continuous, the situation will change a little bit. For a simple span, m is 1. For continuous from one end, it's 0.87. For continuous from two ends, it's 0.76. So this R will, for an R of 1, both are equal actually. It's alpha 0.35 and beta is 0.35. Alpha is the factor for the shorter dimension and beta is the factor for the longer dimension. However, if the longer dimension is significantly larger than the shorter dimension, then alpha will be equal to if it is double, alpha is 0.85 and beta is 0.08. So actually this will show us that it's actually starting to behave as a one-way slab in such a case. And you have a lot of numbers in between. So here MA is W alpha times A squared over 8 if it is simply supported here for sure. MB is W beta B squared over 8. And this over 8, it could be over 10 or over 12, depending on whether it's simply supported or continuous or whatever case we have. So when we go to the code provisions of type two-way slabs, actually there is a limitation for the thickness. So the thickness is, for a simple span, it's the shorter dimension over 35. For for a continuous from one end, it's over 40. For continuous from both sides, it's over 45. And of course, there is another limitation depending on the total perimeter, which is this is a secondary limitation. It's mainly because of the deflection. However, the code allows us for two-way slabs to have a thickness of 100 millimeter, not 120 millimeter, because now both directions are contributing. So actually, you could have a two-way slab with a thickness of 100 millimeter. The minimum reinforcement is for both types of slabs actually is 0.6 BD over F yield. At least 1/3 of the reinforcement should cover all of the span. The maximum bar spacing is 0.2 meters. The minimum bar diameter is 8 millimeter. So actually, you should always have 5 or more bars per meter width. The second reinforcement should be at least 20% of the main reinforcement, and the slab thicker than 160 millimeter, an upper mesh of more than 20% of the main steel, and at least 558 per meter should be applied. Let's have a fast example here. If you have this slab 5 meters by 6 meters, it weighs 1.5 kilonewton per meter square. The live load is 3 kilonewton per meter square. FCO is 25 megapascal. F yield is 360 megapascal. The beam width is 150 millimeters. The dimensions, the slab is, as it is simple, the thickness is 5000 over 35. This is 143 millimeters. In such a case, you take the thickness as 150 millimeters. So the clear span in one dimension is 4.75 and in the other dimension is 5.75. So in one dimension the clear span plus TS is 4.9 while 1.05 times it's 4.99, so it's more than 4.9. So since it's 4.99, it's just less than 5 there, therefore it's okay. And as I mentioned before, for simplicity, if you are in a hurry or in an exam or something like that, you don't need to do this calculation for the L clear. You just get me the 5 meters. So the effective length is simply equal to the length. Same thing in the y direction. Okay, so in the y you will find that it is 6.04, which is just more than 6, so you will take the 6. Okay, so again, you simply take the span in such a. The load calculations, W ultimate is 1.4 dead load plus 1.6 live load, so this will give us 12.15 kilonewton per meter square. Since R is equal to 6 over 5, therefore alpha is 0.45 and beta is 0.25. You could think about this that 0.45 and 0.25, if it was a one-way slab, the 0.45 would have been a 1. So you are actually saving in one direction, you are saving 55% of your moment. So this is 55% of your reinforcement. So in the M alpha will be alpha W, the MA will be alpha W ultimate A squared over B. This is 17.02. The MB is beta W ultimate B squared over 8. This is 13.67 kilonewton meter. So when looking at the main direction, what you should be careful here is that the main direction, because it is the main direction, the cover is only 25 millimeter. Okay, so you get the depth is 150 minus 25. This is the cover. So in such a case, AS minimum is 208 millimeter square. When you do the R1 omega calculation, you get an AS steel of 443 millimeter square, which is more than 208 millimeter square. So this is 6510 per meter. For the secondary direction, one of the major differences here is the cover. The cover is not the 25 anymore because you have a diameter of a perpendicular bar, which is 10 millimeters, so 150 minus 35. This is 150 millimeters. So now you'll get 0.6 times BD over F yield. This will get us a 192 millimeters square. So R1 omega calculation will reach us an AS of 391 millimeters square. So now we'll use 5 per meter in this direction, which makes sense that the secondary direction should always be less than the main direction. So if you find vice versa, then you should feel something that there is something wrong. Okay, if you get the secondary dimension more than the main direction, so that means that there is for sure something wrong. Okay, thank you.